For 50 years, the Nobel Conference at Gustavus Adolphus College has hosted preeminent scientists, theologians, and ethicists to discuss deep questions in the intersection of science and society. From the newest results in physics, chemistry, and biology to the newest fields of multidisciplinary study, scientists at the Nobel Conference have examined the universe at its largest and smallest scales, explored the oceans, and described new materials. Conference speakers have debated the mechanisms of aging, as well as science and economics of food. Often, speakers have given us a glimpse of the next big questions and how they might be answered. Throughout all of the conversations, ethicists and theologians have grounded the science in a human dimension. The 50th Nobel Conference at Gustavus is celebrating a half-century of bringing breakthrough science to lay audiences in the upper Midwest, across the country, and recently around the world. Nobel Conference 50 is assembling previous Nobel Conference participants to look at recent advances in future directions in the physical sciences, evolutionary biology and ecology, medicine and physiology, and the intersection of science and public policy. Stephen Weinberg, considered by many to be the preeminent theoretical physicist alive in the world today, was awarded the Nobel Prize in Physics in 1979 and the National Medal of Science in 1991 for his research on elementary particles and cosmology. Dr. Weinberg currently holds the Josey-Welch Foundation Regents Chair in Science at the University of Texas in Austin, where he's a member of the Physics and Astronomy departments. We hope you enjoy this year's presentation by Stephen Weinberg entitled Glimpses of a Hidden World.
Please welcome Professor Weinberg.
Thank you very much for that kind introduction, and good morning. I'd like to start with a quote from Isaac Newton that expresses a view that's very much in line with what I'm going to be talking about today. In 1704, Newton published his Optics, in which he presented his theory of color and much else. And one of the other things in the book was a foreshadowing of what the future would be like for physical science. Newton knew, of course, about gravity. Nobody knew more about gravity than anyone else. He knew more about gravity than anyone else. And electric and magnetic forces were known since antiquity. But he knew that there had to be more than that, something that acts at very small scales and that gives matter its properties and its stability. And this is what he said. The attractions of gravity, magnetism, and electricity reach to very sensible distances, and so have been observed by vulgar eyes. And there may be others which reach to so small distances as to escape observation. In other words, there are forces in nature whose range is so short that we don't normally observe them, but they're there. And Newton felt they were very important. Newton, of course, had no idea of the scale at which these forces act. We know now that they are forces called the strong nuclear force, which holds protons and neutrons together inside the nucleus of the atom, and the weak nuclear force, which is too weak to hold anything together, but which allows protons to turn into neutrons or neutrons into protons, spitting out other particles, electrons and neutrinos in radioactivity. The range of these forces, as Newton anticipated, is indeed very short. It's so short that they're only felt inside the atomic nucleus. Newton couldn't have known it, but there was a huge gap between the scale of distances that he experienced in his everyday life, say, for example, his own height, and the size of an atomic nucleus. Newton's height is larger than the radius of an atomic nucleus by a factor of roughly 10 to the 15, a 1 with 15 zeros, or in other words, a million billion. And it took a long time, not until 1911, I believe, before that became known. In the 1960s and 1970s, Newton's anticipation became justified. A theory was developed, the so-called standard model of strong, weak, and electromagnetic forces that describe all the forces that have ever been observed acting within atoms or molecules or atomic nuclei. It's a theory that's quite successful in comparison with observation. Nevertheless, we have glimpses of a hidden world beneath this level of the standard model, of things going on at very much smaller scales of distance than the size of an atomic nucleus. And in particular, we have three clues for this hidden world. We're in a better position than Newton because at least we have some idea of the scales involved, very small scales of distance. The first has to do with the unification of the forces I mentioned, the convergence of their strengths at very short distance. The second has to do with the weakness of gravitation, and the third has to do with the masses of the particles I mentioned, neutrinos, which are emitted in certain kinds of radioactivity. And I'll treat these one at a time. The first has to do with the convergence of the interaction strengths of the different forces of the standard model. As I said, these forces are the strong nuclear force, which incidentally also holds quarks together inside the neutron and proton, as well as holding the neutron and proton together inside the atomic nucleus, and the weak and electromagnetic forces, which are unified. There are three numbers that describe the intrinsic strength of these forces. They're called coupling constants. And these numbers depend on the energy at which, on the scale of distances at which measurements are being made. The strong forces are quite strong at long distances. In fact, they're so strong it's impossible to pull quarks apart, but rapidly lose their strength as you go to shorter and shorter distances. The electromagnetic and weak forces are described by two of these numbers, and they vary much more slowly with the distance at which observations are made. Now, when you look at this graph, you wonder if I continue it way out, if I take a much bigger piece of paper and draw the graph all the way, will these come together? Is there some scale of distances at which all these interaction strengths become equal? And indeed there is. This calculation was first done in 1974 by Howard Georgi, Helen Quinn, and myself. And we found that these interaction strengths converge to near equality at a scale which is 10 to the minus 17th of a nuclear diameter. That is 10 million billion times smaller than the size of a nucleus. A really small scale. Now, can we look into things at this scale of distances? How much would it cost to build an accelerator which could probe these tiny distances? Well, a lot. The problem is that you would need photons or other particles with wavelengths that small, a 10 million billionth of a nuclear diameter. And the energy you'd have to give to such a photon to get it to have such a small wavelength would be about 10 trillion times larger than the energy reached in the highest energy accelerators we have today, particularly the Large Hadron Collider in Switzerland. Even if the whole human race was so foolish as to devote all of its economic resources to the purposes of fundamental physics, which I by no means advocate, we would not know how to reach that scale of energies. And so one is tempted to the conclusion, forget about it. But that's premature. There are other clues to the very small scale of distances. Another clue has to do with the weakness of gravitation. I can demonstrate that by pointing to this cup of water which is sitting on the table. Every atom in the Earth is attracting this cup downward, and they all act together to pull it down toward the center of the Earth. And yet, the electrical forces within this table, between the atoms in the tabletop, are able to resist that, so that the water sits comfortably on the tabletop and doesn't fall through going down toward the center of the Earth. You can put this a little bit more quantitatively. Imagine how weak the gravitational forces between two elementary particles. It's incredibly weak. No one has ever observed gravitation inside an atom or a molecule or a nucleus. How heavy would the particles have to be? Suppose you imagine giving a proton or an electron enough mass so that the gravitational attraction between them would balance their electrical repulsion. How heavy would they have to be? Well, they would have to have a mass so large as to contain an energy of a little more than 10 to the 18th GeV. This is called the Planck energy. And you'll notice that this is not that much larger than the energies I was talking about that you would have to explore to see the convergence of the strengths of the weak electromagnetic and strong interactions. One here, the convergence is at something like 10 to the 16 GeV. GeV, by the way, is just the standard unit that we use. It's the energy contained, it's roughly the energy contained in the mass of a proton or a neutron. The convergence is at 10 to the 16 GeV. The Planck mass, where gravity becomes a strong force, as strong as the others, is about 10 to the 18 GeV. And when we're talking about numbers that large, let's not quibble about 100 GeV, more or less. So this suggests that not only do the weak, strong, and electromagnetic forces come together at these very high energies, but gravity, too, at these energies has a strength comparable to theirs. In fact, when Georgie, Quinn, and I wrote our paper, we noted that the energies we were talking about were similar, but somewhat less than the Planck energy. And this was important to us because if they were equal, then the strength of gravity would have invalidated our calculations. So we were relieved. Now, there's a third clue, which is harder to explain, having to do with the mass of the neutrino. Neutrinos, for a long time, had been thought to be massless, and then it was discovered some years ago that neutrinos do have masses. It shows up because of the oscillations of neutrinos of one type in flight into neutrinos of another type, something that is proportional. The rate at which this occurs is proportional to the difference in the squares of the masses. So it gives you some clue as to what neutrino masses are. They're not well measured yet. They're roughly in the neighborhood of a little bit less than an electron volt, or roughly a millionth the mass of an electron. But we don't know precise numbers. But they're definitely not zero, and they're definitely very small. Well, in order to explain what this has to do with a hidden world, I have to provide a brief digression on fundamental constants and how we analyze the units of equations in physics. Let me take an example. It's been known since the beginning of the 20th century that the distance traveled by light is always proportional to the elapsed time and is the same for a given elapsed time, whatever the circumstances. How do we write this as an equation? Should we say distance is 186,000 times the time? Or maybe the distance is 300,000 times the time? or maybe the distance is equal to the time. All of these statements are not only wrong, but meaningless, because statements like these have meaning only if you specify the units involved. And for that reason, we say it a different way. We say the distance is a constant, c, the speed of light times the time. And c, the value of c depends on the units you use. It's 186,000 miles a second, or 300,000 kilometers a second, or 1 light year per year. Depends on the units you use for distance and time. This way of writing equations is surprisingly new. In fact, writing equations is surprisingly new. There are essentially no equations in Newton's Principia. In the 16th century, Huygens used Römer's data to conclude that light takes 22 minutes to cross the orbit of the Earth, but he didn't calculate a speed of light or introduce a symbol for it. And similar remarks apply to Newton's constant of gravity. It took a long time, not until the end of the 19th century, before physicists got used to introducing symbols for the fundamental constants of nature. Of course, we're used to it now. Today we use, most of us who work in elementary particle physics use a system of fundamental units in which the speed of light and Planck's constant, which is the fundamental constant of quantum mechanics, are both 1. And those units allow simple relations between masses, distances, and so on. For example, in these units, 1 electron mass can be written as 1 divided by 3 or so times 10 to the minus 11 centimeters. A decimal point, 10 zeros, and then 386. And so we freely go back and forth between units of mass and distance, and with the speed of light equal 1, of course, between mass and energy. Now, the next point has to do with this, but it goes further. In the standard model, as in the earlier theories of Maxwell and Dirac, all the field equations are simple. And they're simple because there are no constants in those theories whose units are length or length square or any positive power of length. And this limits the number of factors of fields or rates of change appearing in these equations. If you, for instance, in Maxwell's equations, introduce not only terms proportional to the electric field, but terms proportional to the square of the electric field, well, the square of the electric field has a unit which is less than, well, the ratio of those, namely the electric field, has units of length square, so you would have to have a constant in the equations with the units of 1 over length square in order that every term in the equation had the same units, because otherwise the equation wouldn't make any sense. So there's a natural principle of simplicity which is enforced by this requirement that no constants should appear whose units are length or length square, or any positive power of length. And Einstein and Dirac were content to just assume that their equations were simple because nature is supposed to be simple. And it's good behavior for a physicist to assume that things are as simple as they possibly can be. I don't agree with that. I think we need a positive reason why a formal mathematical simplicity occurs in our theories. For a while, we thought there was a positive reason having to do with the appearance of infinities in calculations. If there are no constants appearing in the equations, in calculating things like the probability of a reaction, you have to sum over intermediate states. And that means, for example, summing over the wavelengths of an intermediate particle, like a photon. Those sums turned out to be infinite. If you cut them off by introducing a minimum wavelength, then you get results in, say, calculating a probability of the form 1 over the minimum wavelength to some positive power, which of course becomes infinite when the minimum wavelength goes to 0. those infinite terms can only appear with a coefficient whose units are lengths to that power, because otherwise you wouldn't be calculating a probability, which has no units. And so banishing terms whose involving constants whose units are positive powers of length seem like a good thing. Well, we no longer think of this way. Because of experience with various theories, our point of view has changed. We now think that all terms that are consistent with symmetry principles, such as Lorentz invariance, which are the real principles of simplicity, all terms consistent with symmetry principles do appear in the field equations. And hence, the field equations are filled with constants involving powers of length. But those lengths are very small. And it can be shown that all infinities in such theories are absorbed in a redefinition or a renormalization of constants. So the old argument that the presence of infinities require simplicity is no longer believed. Now, coming finally to neutrino masses, the electroweak interaction energy contains a term, or could contain a term, which is consistent with all symmetries. It's a term involving the square of electron or neutrino fields, the square of the so-called Higgs field, and it has to have a constant in order for the units to come out right, which has the units of length. It has to be a small length, which I've written. I can't point to this here, but it's the thing at the end of the equation, L. We know the value throughout space of the Higgs fields. It's 247 GeV. And so we can calculate what the length has to be in order to give the kind of neutrino masses we observe. And that length is equivalent to an energy of 10 to the 15 GeV. So we have another glimpse of a fundamental physics at a scale which is somewhere in the neighborhood of 10 to the 15, 16, 18 GeV. What is the physics at this fundamental scale? Well, we don't know. It may be a string theory. A lot of people have been working on that idea so far without great success in connecting with observation. We can't test these ideas by building bigger accelerators. Even I know that. But we do have one way of possibly getting a hold on these things, because in the very early universe, before what's now called the ordinary Big Bang, we think there was a period of inflation in which typical particles had wavelengths or had energies like the energies we're talking about, or wavelengths like 10 to the minus 17 to 10 to the minus 19 nuclear radii. And we can observe relics of that very early time. Recently, there was an announcement that gravitational radiation had been observed from that very early time, which would imply that the typical scale of energies at that time was indeed 10 to the minus 7, well, the typical scale of wavelengths was indeed 10 to the minus 17 to 10 to the minus 19 nuclear radii. It isn't clear whether that experimental result will hold up, but we're not completely without weapons that can open up this inner world and tell us something about it. Thank you.
To respect Dr. Weinberg's time, we're going to ask the panelists to do a brief question and answer right now, and then I'm sure that we can forward a few questions to Dr. Weinberg. My question to start off with is, if it turns out that that background radiation gravitational wave experiment does not stand up, what do experiments like LIGO coming back online in 2016 with more resolution or more power, how does that affect? Is that some way we can get at these, or have evidence for these lengths that we're talking about?
Gee, I wish it did. LIGO is a wonderful instrument, especially as it's being improved, and it's very likely that it will be able to observe spectacular events like the coalescence of two neutron stars, or a neutron star and a black hole, which produce incredible amounts of gravitational radiation, which could even be detected here on Earth. Unfortunately, LIGO, as far as I know, has no capability of observing gravitational radiation from the Big Bang or from the era of inflation, and we can't look to that. In fact, the observations which I referred to are not really observations of gravitational radiation. They're observations of microwave radiation. Its polarization is a measure of the way that matter was moving at the time this light was emitted, about 380,000 years after the Big Bang. And that pattern of motion is influenced by gravitational waves. So it's a highly indirect diagnostic for gravitational waves. It's conceivable that we may be able to observe very high frequency gravitational waves from the era of inflation, but I don't think LIGO is in that business.
Steve, this is Harry Gray.
Hi.
I remember having dinner with you a few years ago. Things have improved
Yes.
since then. Would you say a little bit more about the experiment that has seemed to indicate that there may be these very, very short wavelengths?
Are you referring to gravitational radiation? Or
Yes. Would you say a
from
little
the
bit
Big
more
Bang?
about the connection there?
Yeah, well, it is known that the microwave radiation that was emitted when the universe became transparent 380,000 years after the Big Bang is polarized. That's been known now for some years, and that polarization is a very good measure of what was going on. Now, there are two kinds of polarization, the E-type and the B-type. Basically, the E-type, the polarization vectors sort of diverge from centers, and the B-type, they go around in circles. The polarization vectors do. It's the only kind of polarization that has been detected is the E-type, which does not necessarily have anything to do with gravitation. The B-type can only be produced by gravitational radiation. So if we see B-type polarization, that means that there must have been a lot of gravitational radiation left over from the Big Bang, which was influencing the pattern of flow of electrons at the time the universe became transparent, and which was imprinted on the polarization in the microwave background. Now, the B-type is harder to see, but the amount of it is a direct measure of the density of energy, or you could say the typical energy per particle at the time that, at a certain time in the past. It's a little hard to say what that moment was, but it was a time during the period of inflation, and probably is not very sensitive to precisely what moment during inflation. Gravity, after all, is produced by matter and energy moving around, and the more matter and energy there is moving around, the more gravitational radiation is produced. The amount of gravitational radiation which would be needed in order to produce the signal which was announced by this collaboration, the BICEP2 collaboration, is such that the energy scale is like the energy scale that I was talking about in connection, for instance, with the convergence of the couplings of the Standard Model, this 10 to the minus 17 nuclear radii distance scale. And that would be the typical distance between particles at that time. Unfortunately, there's something else that can produce a B-type polarization, which is of no fundamental interest. Well, it's interesting to astronomers, but you know, they get interested in all sorts of things. It's dust. Right. Not at the time of inflation or the time of the Big Bang or 380,000 years after the Big Bang, but relatively recently, a few billion years ago, recent as the universe goes. And that dust can produce this effect. And the big question now is whether what we're seeing, what they're seeing, I'm not seeing anything, whether what they're seeing is an effect of dust or an effect of gravitational radiation produced during inflation. And we don't know yet. There are groups like the Planck collaboration in Europe that will be announcing soon their analysis of their data, and then we'll get a good idea.
That's what I was wondering, whether there are other groups that are looking at this now.
Oh, there are a number of groups.
We'll know this answer fairly soon.
Yes, I think we'll know it before the end of this calendar year.
Great. Thank you, Steve. Are there others?
I was blown away by your talk, but as a geologist, I find there's very little I either understand or can know to help. I'm just wondering, this looks like an astronomical and cosmological problem of measurement and consideration of the inner world beneath. Is there anything in the earth sciences that can help constrain that inner world at such an extremely small scale? I think the simple answer is probably no, but I haven't thought about this, and maybe you have.
Well, I think there is, in a way, indirectly. By the way, I'm sorry you said you didn't understand my talk. I was trying to make it understandable, but I guess I failed.
Well, there were others that did it better.
I hope you don't think that was a compliment.
I'll try not to.
In the spirit of this program of including all possible terms in the field equations that are consistent with symmetries, whether or not they're multiplied by constants with the dimensions of length, there are other terms which produce not only neutrino masses, but other effects like the decay of protons and neutrons, which are otherwise stable. Neutrons are stable inside atomic nuclei, as far as we know, and because nuclei last, and protons, as far as we know, are absolutely stable. But it's now thought that it's very likely, because of these other terms, assuming that the scale of distances is similar to what I've been talking about in my talk, that the decay rate of the proton and neutron are not zero, they're just very small. And the only way to measure that is to go deep underground to get away from cosmic rays with big tanks of water or whatever liquid the experimentalist chooses, and wait a long time for an occasional proton or neutron to decay. The background is the radioactivity from the Earth. And Earth science is needed in order to anticipate the kind of background that will be observed, because radioactivity produces things like photons and neutrons, and those can imitate, unless you're very careful, the kind of proton decay that you're looking for. Obviously, enormous progress has been made in the earth sciences, which doesn't rely on progress in fundamental physics. The theory of continental drift, I don't think, owed anything to the work of elementary particle physicists. And that's just something we elementary particle physicists have to get used to. We're not very useful.
Well, we sometimes feel the same way. Thank you very much for the answer.
Good morning. I want to ask you a question that is really sort of to the side of what you've been discussing, but I think you'll be able to help me. For those of us who are interested in the brain and how it is that conscious experiences are produced by the brain, we're often met with a certain kind of skepticism about consciousness. And the skepticism takes the form that it really has nothing to do with the brain, and that ultimately, because physics is so weird, and because consciousness is so weird, that maybe they're the same problem. And I would just like to see how you answer that question.
Oh, gee, that's a hard one. I mean, there is something about consciousness which is hard to ever imagine coming into the ambit of ordinary natural science. That is, we may find correlations between things going on in the brain and our conscious experience, but how do we ever express in impersonal, naturalistic terms what it feels like to see the color red? Philosophers call this the problem of qualia. I don't know, I don't have any good answer to that. On the other hand, I don't think the problem has anything to do with the weirdness of physics. I could be wrong about that. Of course, quantum mechanics and relativity underlie everything in nature, but there are scales of experience in which the effects of the departures from ordinary classical Newtonian physics are very, very small. We don't worry about quantum mechanics when we study thunderstorms, another thing we don't understand well, by the way. But we don't think it has anything to do with quantum mechanics. And in the same way, brains are complicated like thunderstorms. And I know some physicists, I believe, well, I shouldn't quote anyone, but I believe some physicists have tried to connect the mysteries of conscious thought with the mysteries of quantum mechanics. I don't believe it. I think brains exist at a scale of chemistry and physics which is much larger than the atomic scale. And although quantum mechanics dictates the way atoms behave, once you know that, I don't think quantum mechanics has anything to do with what's going on at larger scales in the brain. As I said, I could be wrong about that.
Great, thanks very much.
Hello, Stephen. I'm Steve Chu. I have a question. The Standard Model has been wildly successful, but many physicists, I included, were hoping to see breakdowns in the first run of the LHC. As the upcoming run of the LHC is about to turn on at higher energies, one still is hoping to see a breakdown of this and something more than just the plain old vanilla Higgs, supersymmetry, things of that nature. But the window seems to be closing. In particular, other experiments like the search for an electron dipole moment have turned out to have negative results. Can you talk a little bit more about what we're hoping for, but also the unease if there is a big desert between where accelerators can reach and grand unification?
Oh my, I couldn't agree more that we were hoping for something completely unexpected from the LHC. If the only thing the LHC does is to verify the Standard Model, including the Higgs particle that it predicted, then it's going to be very disturbing. Well, from Newton's time to ours, it's a little bit more than 300 years. Maybe we have to wait that long. I don't know. Cosmology, as I said, provides one way of getting to really small scales. But there is one reason for hope. Astronomers tell us 5/6 of the mass of the universe is in the form of some kind of dark matter particle, which is an ordinary particle. It moves around slowly. We don't know its mass. We know the density of mass that it provides in the universe, but we don't know how much mass there is in each particle. And those dark matter particles are are there in the universe. I mean, there's so much evidence for it now. We were hoping that dark matter particles would be produced at the LHC. So far, there's no evidence for that. We don't know whether their mass is small enough so that they can be produced when the LHC goes to higher energy. Some of us were strongly advocating a larger accelerator here in Texas, a few hundred miles north of here in Ellis County, called the Superconducting Supercollider, which would have had 3 times the maximum energy of the LHC. It would really be a terrible irony if the dark matter particle turned out to have a mass just in the range that could have been produced at the SSC, the Supercollider, and not at the LHC. But of course, I don't know that that's true. I don't know. It's going to be hard if the LHC doesn't discover something really new. I'd be just happy with more Higgs bosons as an indication of something new. They are required in supersymmetry theories. But for the reason of frustration which you've expressed, many of us have turned our attention more to cosmology these days, where there are, as I've been discussing, observations that are really relevant to fundamental issues and things that can be done theoretically. Cosmology is now in a very exciting phase. Physics, elementary particle physics is too, but that might not last.
Thank you.
Thank you for your time, Dr. Weinberg.
Well, thank you for those very good questions. If I may, I'll hang around and listen to Dr. Gray.
We will take a very brief break so you can stand up and stretch while we change technology out.